Okay, so switching gears a bit from your OP1 presentation, let's go back to algorithms for milestone 3. So we were talking yesterday about breadth first search. We saw that it seems much more logical for search in a graph where we're looking for shortest paths than depth first search. And we saw that we could actually get optimal answers out of it if we code it properly. Let me just pin my video here so it shows up fine. All right, there, I've got the right view now. Okay, so breadth first search was searching the graph more efficiently, but let's look at what the complexity of it was. The basic structure of breadth first search is we had this wavefront, the list of nodes that we need to process next. We've reached them, but we haven't processed them. We haven't looked at what comes after them. So that's our wavefront. So while this wavefront is not empty, we're going to go and keep doing work. Now, the code I showed you yesterday did not use a visited flag. When we did depth first search, we used a visited flag to avoid ever visiting a node more than once and to avoid going in circles. If we used a visited flag, so we have some data structure per node and we put a .visited flag inside of it, then we'll only visit a node once. And that means this while loop that's going to do some work for every node can only execute n times. The work in that loop, if you remember back to last week, was order 1. We just looked at the edges coming out of that node, so what could we reach, and did a little bit of work to push each of them into a list or a queue. So that's order 1 work, which means this would be order n. So n is around 100,000 for a typical city. This is hard for you to estimate, but we can execute an instruction in about a nanosecond on a modern CPU or a little less. So that loop has maybe 100 instructions in it. So this is maybe 10 to the negative 7 times 100,000. So it's going to be less than 1 second. And really we should go measure that, but we can tell it's going to be pretty fast. So pretty fast algorithm. But with this node.visited flag, this is actually not a good idea. I didn't show that to you in the code yesterday for a reason. Because it only visits a node once and never will look at it again, we won't get the shortest path, right? We went through some examples where you could see you got to code breadth first search pretty carefully or you won't get the best path. Then we did code it that way. So with re-expansion means if we reach a node, we check is the travel time, the best travel time we ever saw at that node, which we stored, is that best time worse than the travel time that we would have if we take this new path, this new way of reaching it that we just got from the wavefront. If the new way of reaching it that we got out of the wavefront is better, so the new travel time is lower than the old travel time for that node, then we're going to say, yeah, let's update it. And that means we need to re-expand it. We need to basically say, okay, we've updated its best time. We've got to take all of the intersections that we can reach from that node, and we need to put them back in our list or our priority queue. So we need to do all the work again. Okay, so that means that we actually could go through this loop more than n times, because we could actually look at the same node multiple times. Okay, this is actually a lot harder to bound the complexity, but it can be a lot slower. I'm not going to try to compute a bound on this one. I'll just demonstrate it. So let me quickly flip over to, okay, I've got a demo going. And let's see, I can never resist showing depth first because it's so bad. So remember, that's where we started. Our recursive has no idea of what it's doing algorithm, so we're not going to use that. So let's switch that out and let's do a breadth first. So you can see over here, I switched the algorithm to breadth first. And I'm just going to click on an intersection. It's going to go find a path. Those ones were pretty close. Okay, so I'll zoom in a little. And it found that pretty quickly. Let's go a little further away, maybe over here. And now you can see it run a little longer. Let's go a little further away still. It's slowing down the further away I get. And the reason it's actually slowing down is, well, it has more work to do, but this re-expansion is actually slowing it down a lot. It keeps finding, as it explores these roads, it keeps finding better paths to certain nodes that it's already reached, puts them back in the priority queue, and it's basically redoing an awful lot of work. So you can see this algorithm is now taking a while. I've slowed it down some with the drawing but it's still not that fast. It's getting close to where I clicked, so it's eventually going to terminate. Okay, now it found the path. So it found the travel path that takes 20 minutes from here to here. But it wasn't, certainly wasn't as snappy as I would have ideally liked. So let me see if I can shrink this down. Okay. Does it just stop once it finds any path? The way we coded breadth first search and what I just showed you, it actually doesn't stop until the best travel time on the priority queue, best travel time in the wavefront, so the list or the queue, is higher than that's higher than the travel time that we've found to the destination. Okay, so it actually, to make sure we get the best answer, we can't actually stop with this algorithm. The first time we reach the destination, we actually have to keep going, keep taking things off of the wavefront until there's nothing left in the wavefront that has a lower travel time than the travel time we've found to the destination. Okay? So that's a good question. Okay, so we've got an algorithm now that will find us optimal travel paths, but it does a lot of wasted work. It does this re-expansion where it can put things in the wavefront over and over again. So this if statement is what is giving us, finding us optimal paths, but it's costing us a lot of CPU. And let me just visualize this more abstractly. What we're essentially doing is we start expanding out in breadth first search from the source in kind of waves. And the wavefront is basically the edge of this circle. It's like our to-do list of what to do next. So we're kind of expanding outwards. We're getting close to this destination here. Looks like we're going to finish soon. But maybe there were a whole bunch of short streets near the destination. So we've been slowly expanding them. And it turns out they were really fast. So now we've found that we found a better path to some node here. And we start re-expanding from it. We put that node in the wavefront, and that actually means we now look at all of the things that node can reach again. So we get essentially more re-expansion going on. We're kind of redoing similar work by looking at the same nodes over and over again. As we find better paths to them, we then put them in the wavefront and look for better paths that include those nodes. Eventually we find the destination and we invoke our backtrace routine and we get our path. Okay, so it does converge, but this re-expansion is very wasteful. Let's see, there's a question of, I don't understand how the wavefront could be empty. The wavefront will actually become empty when you've looked through the whole graph. Like when you've looked at all of the nodes in the graph, and with this re-expansion, you could actually look at them multiple times, but eventually, when you can't find any shorter paths to anybody, your wavefront becomes empty. So that's the answer to Mark's question. Okay, so this is the code that we have. So our breadth first search path searches from our source node to our destination ID. We're using a linked list as our wavefront. And just to remind you of what it's doing, we keep taking, as long as the wavefront's not empty, we keep taking things out of the front of the wavefront, so the front of this linked list, and we check what we just took off. So for example, I took off node 78 with a travel time of 20 seconds. So I would check, well, if I look at node 78 and I get the best time that I've stored to it, is that less than 20 seconds or not? If it's not less than 20 seconds, then I'm going to go do a bunch of work. I'm going to basically update the best time that I've ever seen to node 78. So I'm going to say its best time is now 20 seconds. And that means that I got to look at all of the neighbors of node 78. So if this was node 78, I now need to look at everything that it can connect to, because maybe this is now going to lead to a better path to them. So I put this node, well, all of the nodes that it can reach, into my wavefront with the travel time that I would get from this node 78 at 20 seconds, plus whatever travel time there was, to get to that new node. Okay, so that's my key loop in this breadth first search, and it's inefficient if it winds up looking at the same nodes multiple times, doing this re-expansion. Okay, so how can I get rid of this? So is there anything I could do that's a bit more clever? So right now, basically, my wavefront is I put things in at the back. Okay, that's here. And I take things out of the front. So it's a queue. Stuff goes in the back, stuff comes out the front. And it is leading to this undesirable behavior that I often am looking at the same node multiple times as I find better paths to it. And that's not too bad, but the problem is I put it, every time I find a better path to it, I put it back in my wavefront, which means I'm going to look at everything that it can reach, and so on and so on. So there's a lot of extra work. Okay, so some ideas in the chat. So check travel time for each edge and go to the edge of least travel time. So it's the right idea, but is it the least travel time for an edge? Okay, so an edge would just be one thing. So I'm at a certain intersection. I've got one edge to another intersection. So maybe this is my intersection 78, and I've got 4 intersections from it. It's just saying, well, pick the edge. It's a good idea. Let's try to look for low travel times. Those are our most promising solution. But can I do that just on an edge basis? Okay, so let's see. Isidore's got an idea of choose target nodes that are closest to the target. That's a good idea, but it's beyond where we are right now. So just looking at this wavefront, what do you think the most promising partial solutions are? Every node in this wavefront represents basically a partial solution. If I trace back through those reaching edges, there was some method by which I got to this node with a certain time. So everything in this wavefront represents a partial solution ending at that node. Okay, so expand, yeah, so Trevor's saying expand the shorter paths first. And yeah, that's exactly the right heuristic. If I look at this, I've got node 2 with a travel time of only 5 seconds. I should actually look at that first before I look at these other, well, this one, which is node 78 with a travel time of 20 seconds. Looking at, so yeah, going through my wavefront and finding what are the smallest travel times in it is going to be a much more organized procedure. Okay, so we're just going to change how we insert things in the wavefront, which is right here, and how we take things out of the wavefront, which is right here. We want to minimize node re-expansion, and we're going to do that by always looking at the smallest travel time in the wavefront as the next thing we take out. All right, so let's look at what that small change, it's not a big change in code. Let's look at what it does. Okay, so we start our search from the source. So we put in our wavefront node 0 with a travel time of 0, because that's the source in the example I'm using. Okay, it's not our destination, so we look at the things it can reach. It can reach node 1, it can reach node 2, so those both go into our wavefront with the travel times to them. Okay, node 2 we could reach with a travel time of 5 seconds. So even though it's not, we might have put it into the wavefront second, we want to look at it next. So we're going to go through the wavefront, we're going to find the smallest travel time, we're going to look at it next. Okay, so we take it out of our wavefront. Once we do that, we'll look at, it's not our destination, we'll look at where it can go. It can go to node 1. And to get to node 1, we had a travel time of 5 seconds. We had another 5 seconds to follow this street segment, so it's 10 seconds. Total, we put that in the wavefront. Okay, now that's actually the smallest time in the wavefront, so that's the one we want to take out next. So we take out node 1, and it's not our destination, so we're going to look at where it can go. It can go here. We put that in the wavefront as a travel time of 16 seconds, still smallest, so we're going to look at that next, and so on, okay? And we're actually going to find quite efficiently that we can get to our destination with a travel time of 19 seconds. And we didn't do any of this re-expansion. There was a longer path that went this way. We never actually looked at it, okay? There's still something in our wavefront, but we're done, right? We've already found, this actually travel time is already higher than the travel time we found at the destination. So it's guaranteed it's not going to be better. So we can stop at this point and just return this path. Okay, the question is, what if A was 8 seconds? Okay, so that's a good question. Okay, so someone is asking, what if this was 8 seconds? It would still work. What would happen is my wavefront would be different. I would have looked at this node first. I would have put these node 1 and node 2 in the wavefront. I would have looked at node 2 second because it's got a travel time of 2. I would have put this node in the wavefront again, but this time I would have put it in with 10 seconds. And now the lowest travel time in the wavefront would have been this node with a travel time of 8 seconds. So that's the next thing I would have taken off, and it would have worked. Okay. From this node, I would basically find this one with a travel time of 14 seconds. I'm eventually going to look at this node again because that's still in my wavefront with another path with 10 seconds. But I still have that code. Let me go back here. It's important to keep this code that if the travel time is not better, I don't do anything. Okay, so all I'm changing is how I use my wavefront. And by always taking the smallest travel time, I get rid of this really inefficient re-expansion. I look at the most promising paths first, and I don't redo all this work over and over again. Okay? And Mark is saying, if you understand correctly, this algorithm basically finds the shortest time between our starting point and all intersections. And yes, that's actually true. So as a side effect of this algorithm, you will find the shortest path, not just to the destination, but actually to all the intersections that you've reached by the time you terminate the algorithm. So, and sometimes that's actually helpful. In some cases, in this case, it's not very helpful that the fact that you actually know the shortest path to a whole bunch of intersections, because we're just asking you to find the shortest path from here to here. I'm going to show you in a few lectures that there's other cases that come up in milestone 4 where that can be helpful. Okay. And I guess Sarah's asking, how likely is this case? Like I showed that basically this enhancement is resulting in less work. It's actually very likely. It happens all the time in general graphs. So I'll show you what difference this makes in maybe a minute. Okay, so this just shows we found the right path and we found it efficiently. Okay, this is actually given a name. So it's a small enhancement on breadth first search. All that we're doing is we're making sure we take the smallest travel time out of the wavefront for when we decide what to do next. The algorithm's important enough, it's given a name. It's called Dijkstra's algorithm after its inventor. Okay, so how fast is this algorithm? So, well, we need to figure out how much work it is to get the smallest element. So right now we're using a linked list in the code I've shown you. And in a linked list, if I've got n things in this list and I want to go find the one with the smallest travel time, how much work is that? Yeah, so it's order n, which is bad. Okay, so if I've got n things on the list, it's going to take me order n to go through it. Okay, so insertion, actually I need to think of two things. I'm going to be putting things in this wavefront over and over again, so that matters, and insertion's good. It's order 1, you just put it at the end. But finding the smallest element, you have to scan the whole list, which is order n, which is bad. Okay? I'm not going to use the number m or the variable m, I'll use m, because the number of things in this linked list might not be the same as the number of nodes in the whole graph. So let's say it's different, it's m. It's number of active wavefront entries. But it turns out that we can actually have a wavefront where we have pretty much all the nodes in the graph in it. So in that case, this would be order n. Usually it's somewhat better. We don't have all the nodes in the graph. It might be more like order n to the 0.5. It's just kind of the edge, but that's still pretty bad. Okay, so because we're gonna put things in this linked list, this wavefront, and take things out many times. Basically, we have a loop where we might go through all of the nodes in the graph by putting them in the wavefront and taking them out. If the work to take it out, find the smallest element in the wavefront is order n, then this altogether is going to be order n squared. Okay, so this order n by itself is not too bad, but order n in a loop, which can happen n times, which is where this order n computation is really bad. Okay, so this isn't very good. I see in the chat there are already ideas of how we can make it better. Yeah, Trevor's saying, is it order n to the 0.5 because the number of nodes in the wavefront is like the perimeter? Yeah, so you're right that the number of nodes when you're using Dijkstra's algorithm, where you're not sticking nodes in the wavefront over and over again, you're doing things in a more orderly fashion, you usually get the number of nodes is kind of like n to the 0.5 because it is basically the perimeter of the area you've searched. So often it's not really going to be order n squared, it'll be order n to the 3/2, which is still not great. Okay, so yeah, it may not be as bad as order n squared, but still not great. Let me get rid of this. Okay, and Isidore's already said, what can we do that's better? And what we could do that's a lot better is a binary tree. So a binary search tree has a fast insert, it's order log n, and it has a fast find smallest. It's also order log n. Okay, so go to a binary search tree, insertion is order log m, and where again m is this number of elements in the wavefront. And removing the smallest is also order log m. So that's much, much better. I mean, we're a little bit slower for insertion, but we're way faster for finding the smallest. Okay, so that kind of repeats what I just did. We're going to go through that wavefront loop n times. We can look at every single node in the graph before we find our destination in Dijkstra's algorithm. The work to remove the next item in a linked list is order n to the 0.5 to order n, whereas a binary tree, it's order log m. And order log m, m is the number of active wavefront entries, is for sure less than log n. So for the linked list, the complexity is somewhere between n to the 3/2 and n squared. And if I take my same assumption of processing one node takes about 10 to the negative second seconds, this is a big range, somewhere from 3.2 seconds to 1,000 seconds. So not that fast, and the worst case is pretty bad. A binary search tree is going to be well under a second. So it's a huge difference to change your data structure. Okay, so that's way better. So we're up to actually a pretty reasonable algorithm now. So Dijkstra's algorithm is order n log n. That's looking pretty good. If we use a proper wavefront, we use a binary search tree. Is there anything better than a binary search tree? Yeah, so Isidore saying priority queue. The priority queue just means you put things in any order you want and they come out sorted. So when you take something out, if you want a priority queue where you basically sort for the smallest value, the thing with the smallest value, the smallest travel time will come out first. Okay, so that's a priority queue. A priority queue is not, STL has something called a priority queue, so you can use that. But what's in an STL, a priority queue? Priority queue is not the name of what is actually the underlying data structure. Okay, so a priority queue is like kind of an interface, and STL has a priority queue, which you can use, but what's in it? It's actually a little better than a binary tree. And I see Trevor saying Fibonacci heap. Okay, actually I see Himanash saying heap as well. So a map, I see a bunch of comments here. So a map is a binary search tree. Okay, that's what STL calls a binary search tree. It's not a bad choice at all. It'll work pretty well. But yeah, we can do a little better. We can use a heap. And a heap you haven't learned yet, but I'll quickly show you what this data structure is. Insertion in a heap is order log n, which is the same as a binary search tree, and removal of the smallest element is also order log n. So far it sounds no better than a binary search tree. But it is somewhat better. Its computational complexity is the same, but the constant is lower. So it'll be faster by a factor of usually around, say 3x, 2 or 3x faster than a binary search tree. Okay, so how does this work? I'm going to show you what's called a min heap. So a min heap winds up with the smallest element is on top. So assume that all these numbers represent travel times. So what I want to do is I want to insert new travel times, and I want to be able to find the smallest one really quickly. So because I want to find the smallest one, I should use what's called a min heap. So a min heap it's like a binary tree. You see every node has two children. So there's one child, another child. The key of the parent, so here's my parent, it's got a travel time of 3. That is smaller than either of its children. They have travel times of 20 and 36, and that's true throughout the whole tree. So this node has children with travel times of 40 and 35. This node has a child with a travel time of 50. So every node you look at in this whole structure, this tree, its children have bigger travel times or bigger keys. But there's no relationship between the children. So in a binary search tree, you also could guarantee that the left child, this one, would have a smaller key than the right child, this one. And that's not true in a heap. You can see here that actually the left child has a bigger travel time than the right child. So it's like a binary search tree, but it's only partially sorted. The parent has a smaller key than the child, but between the left and right children, there's no relationship that is guaranteed. This is really good for priority queues because in a priority queue, all I want to do is be able to insert things quickly and get the smallest element quickly. And I know where the smallest element is. The smallest element is right at the root of the tree. And that's all I need for a priority queue. I don't need the full sorting that I would get in a binary search tree. Okay. So how does it work? You don't have to code this by hand. It's in STL. STL has a heap, which you can use. It also has a priority queue, which its underlying implementation is a heap. You can use either of those two things. You don't have to code this, but it can be useful to understand how does it work. So let's see how a heap works. So in a priority queue, I want to take the smallest element. So let's say I say pop off or remove the smallest item because I'm going to go process it. I want to take it out of my wavefront and do something with it. Okay, so what it does is you pop off the top item. So you say remove it from the heap. I'll go process it now. And this isn't a heap anymore. The smallest element is no longer at the top. So next time you come back to the wavefront saying, okay, give me the next thing, it's not there. So we need to fix it. We need to make this thing back into a heap. And the way that can be done with a small number of operations. So you take an element from the bottom level of the tree. So that will be a large element like this. And we just move it to the top, which is clearly not the right place for it, right? That's supposed to be the smallest element, and that's not the smallest element. So now we have to do some more fix up. We compare it to its children, and you swap it with the smaller one of its children, if necessary. Okay, so we compare 50 to its children. So is 50 less than 20? Is 50 less than 36? It isn't. The smallest child is this 20, so we swap with that. Okay. Now we have to compare those children again. We have to compare it to 40, compare it to 35. Is it smaller than them? It's not. If it's not, swap it with the smaller of the two children. Okay, so the smaller of the two children is the 35. So we're going to swap with that. And now we're done. This is actually a heap again. All right, so how much work was this? This is a binary tree. So it is log n levels, which means that the number of comparisons and swaps we just did is log n. So this is order log n work, but it's less work than you would do by a constant factor, by a factor of 2 to 3 usually, versus what you would do in a binary search tree, where you have to keep the whole thing perfectly sorted. So it's a bit faster. And yeah, so Dan, you're asking, isn't this order n worst case? It's order log n worst case, because I'm not going to look at every, if you go back and watch what I just did, I only compare to my children. So I'm going to do one comparison to these children, and then I'm going to do another comparison to these children over here. And if this tree was huge, if it had a million nodes in it, it still only has 20 levels, and I would only compare to my children 20 times, not a million times. Does that make sense? And there is no case where you do more. You will only compare to your children, and the number of times you have to do that, the number of levels you go through, is logarithmic in the size of the tree. Okay, so let me quickly demonstrate that. Yeah, a heap is balanced actually. So Dan is asking, could this be, the heap is kept balanced. So it turns out that the implementation of the heap will keep it balanced. Okay, so let's see. Let me remind you of what the breadth first search looks like again. So let's see, let me do this one. That was a bit too fast. Let's go over here. Okay, this is my breadth first search, and it tends to slow down as I approach the destination because of all the re-expansion that you can't see. Keeps finding better paths to some of the things way back over here, and it's slowing down. But eventually it's going to get there. Okay, so find the path. So I'm going over here, I'm changing my algorithm. So now it's Dijkstra's algorithm. So it's not much code change. I'm just going to sort my wavefront, and I'm sorting it with a heap or a priority queue. Okay, so if I click, you probably barely saw that. Okay, so let's zoom out and do like something that's further away. Okay, whoops, too much zoom. All right, so let's go over there. So we're still slowing this down so you can see it in the graphics, but it's pretty fast now. And actually zoom is making it difficult to see because there is a bit of a lag. But so the expansion is a lot faster, okay? So this is when you're doing milestone 3, start with Dijkstra's algorithm, okay? The reason that I've shown you these algorithms is, well, the reason I showed you breadth first search is that it is the underlying implementation for Dijkstra's. They're very closely related. And let's see, I think I might have accidentally stopped sharing. All right. Any questions on that? Okay, so let's see if we can do better. And let's see. So can we do better in Dijkstra's algorithm? And the answer is yes, we can. Okay, so let's see what Dijkstra's is pretty good. It's a pretty good algorithm, but it does have some drawbacks. So this may be easier to see if I just do it in a cartoon again. So it's expanding outwards. You're seeing this wavefront gradually appear, and it's not doing a lot of re-expansion of nodes as it finds better paths. So it's much more orderly and much faster. And it finds our destination, and we call our backtrace routine, and we find it. We mark the path. Okay, so that's pretty good. But one thing you'll notice is that we do a lot of work that seems kind of unproductive. We're here, and we spend a lot of time looking at nodes that are actually in the exact wrong direction. And it seems pretty unlikely that our best travel path is going to go in the wrong direction and then eventually loop back over here. So we do look at more of the graph than we're probably going to need. Okay, so how can we do better? The basic way you do better than Dijkstra's is you're trying to get rid of some of this. Okay, this doesn't look so good. Don't look at those nodes because they're less likely to give a promising solution. But we still want to make sure we get the best path. So how can we do that? Yeah, and Sona's got a good. So there's a bunch of discussion here that's good. So Isidore is saying use distance heuristics. So yeah, I can use some heuristic that am I going in the wrong direction? If I'm going in the wrong direction, maybe I shouldn't go in that direction. Although Sona's got a good point as well of, well, what if there's a highway over here? So yeah, maybe I'm going in the wrong direction, but maybe then I get onto a highway that goes right up to my destination. So, which is a good insight. So we have to be pretty careful if we want to guarantee we get the best path, that we're not too aggressive in saying for sure it's not in this direction. Isidore is saying instead of sorting by speed in your priority queue, why don't you sort by distance to the target nodes? And that is a good idea. So let's examine that. Okay, it's a very reasonable idea. So I actually have that on the slides. What if we only look at nodes that take us closer to the destination? Which isn't exactly what Isidore is saying, but it's kind of related. So we're not going to bother going in the wrong direction. And I could code this up by saying, let's check if my distance to the destination is of the node I'm at. So here's some node, and I know how I got here. So here's the node I'm looking at. Here's the node I came from. I'm not going to spell predecessor, but that's what it is. If it's closer to my target, so here's my target or my destination, then I'll process it. But if not, I'm I'm not going to put it in the wavefront, or I'm just not going to do any work for it. I'm going to disregard it. Okay, so that seems like a reasonable way to do things. But as Sona said, you got to be careful about highways. So this actually seems reasonable, but is too aggressive. And here's an example. Like, let's say I want to go from this node to this node. So the best path is actually go left for a while, go up, go across, and come around and go there. If I said that I can never go further away from my destination, I would never have actually looked at this first part of the path. I would have said, well, there's no point in doing that. I'm going further away from my destination. I want to go that way, but I can't go that way. There are no paths that are going to go across the 401. I have to go over until I get to an underpass and follow the streets to get to my destination. So if I actually coded never look at a node if its distance is greater, distance to the target is greater than its distance from its predecessor to the target, I would have actually said this is impossible. I would have returned a zero length path and frustrated my users and failed the unit test. Okay, so yeah, so this is too strong. Can't do that. Okay, so we'll talk about this on Wednesday, but the way that you can go, well, maybe I'll show you a quick overview of this. You can do better than Dijkstra's algorithm with what are called A-star algorithms. A-star algorithms use domain-specific heuristics. So we're working in a city map, which means that we know more than just the graph connectivity. We also know the location of the nodes. Okay, so we don't just know I have a node here, which is some intersection, and we know its adjacent intersections. We know all of that, but we know more. We also know the position of this intersection and the position in space of these other intersections. And we know the position in space of our target, what our destination is. That means we can estimate whether we're getting closer or further away for each of these nodes to our destination. And that's helpful. We can put some extra smarts into our algorithm. What we're going to do is we're going to incorporate this additional information into the wavefront sorting, or the ordering in the wavefront. So we don't want to do what we did here, which is we're just going to have a hard pruning function. We will not look at something if it appears to be in the wrong direction. It's too harsh. It's going to miss cases where we have to go in the wrong direction for a while, etc. We're going to do something softer. We're just going to sort our wavefront so that the most promising solutions come first, and we look at them first. We have to be a bit careful about how we do this, because we have to make sure that we look at all the promising partial solutions so that we are going to get the best answer. So we have to do this a little bit carefully. And another name for these A-star algorithms is called best first search. So we start out with depth first search, which kind of wanders around recursively and randomly in a graph. Breadth first search, which expands outwards in waves. And now best first search essentially is like breadth first search, where it expands in waves, but it prioritizes the most promising solutions, partial solutions to look at first. Okay, and if I show you a quick picture of this, what it will do, by sorting our wavefront, we want to make it explore preferentially towards our target, our destination. We're still going to do some exploration in the other direction. Okay, we can't perfectly say what should we look at next. We can only sort all the promising solutions and make sure we look at all of the things that could possibly lead to a best path. But we can reduce the amount of work that we do in kind of unlikely directions, which is with Dijkstra's, we would have expanded all these nodes over here, and with A-star, we won't. So we'll be more targeted, we'll do less work, we'll still find an optimal path. Okay? Yeah, so it mostly explores in the right direction, but it explores broadly enough that if you code it correctly, it still can guarantee that you get optimal paths. And it can go around blockages like the highway that I showed you before. Okay, so that's it for today. We'll talk a bit more next week about, well, what are some possible A-star heuristics and how do you modify Dijkstra's algorithm to do that? A-star is not much extra code on top of Dijkstra's algorithm, and Dijkstra's algorithm is not much code change versus breadth first search. So In the lab next week, if you've got your lab session before Wednesday, you can, and you aren't quite sure what to do about A star, code Dijkstras. The code changes from Dijkstra to A star are quite small. It's mostly thinking, not that much coding. Okay, so I'll stay on the line in case there are questions, but that's all the content I had for today. Okay, so I'll answer a couple of questions here. Are we going over algorithms on Thursday of next week? So I'll finish off M3 algorithms in the first part of the Wednesday lecture. It won't even take us the whole lecture because we're getting close to it. I'm just going to give you some hints and ideas on A star. Then we'll move on to milestone 4, which you're not going to be coding yet, but it builds on top of milestone 3. So we'll go over like what are the algorithms that you can, a different class of algorithms that you're going to use to attack milestone 4. And that will be the second half of Wednesday's lecture next week and all of Thursday's lecture. There's a couple questions on what do you need to pass all the M3 performance tests. A decent A star algorithm will pass. Okay, so A star is a family of our algorithms, because I'll show you this next week. But there's A star is all about how you sort your wavefront. So you can come up with different ideas of how you might do that. So A star is like a concept rather than one exact algorithm. If you do a reasonable A star algorithm, it will pass all the tests. If you write a Dijkstra's algorithm that is very well coded, you can pass all the tests too. We set the test, the hardest test is set to 2.5 times the CPU time of a reference solution. And our reference solution uses A star. So you can write a pretty sloppy implementation of A star and pass, or because A star is only somewhat faster than Dijkstra, if you've got a very well-coded version of Dijkstra, you can usually pass as well. But it's easier to do with an A star. Let's see. So do I think it'd be worth it to optimize M3 far beyond the performance test for the purpose of M4? It's not really worth it. M4, you need a reasonable pathfinding algorithm. Doesn't have to be perfect. Doesn't have to pass all our speed tests. Doesn't have to be optimal, actually. Doesn't have to pass the optimality tests. And you're not going to get that much mileage out of making it a bunch faster. So I personally wouldn't worry about it a lot. It's not going to help you a whole lot with milestone 4. And actually, there was another question from last lecture that I don't think I answered of, are the performance tests public? And yeah, the performance tests are all public. So it's kind of easy, medium, and hard. And we will run private performance tests too, but they're set in exactly the same way. So if you pass the public performance tests, by more than an incredibly tiny fraction, then you're going to pass the private ones because they're not any harder. They're just run on different cases to make sure you didn't try to overtune or hard code something. Okay, actually, Mark is asking, is STL priority queue better or heap? STL priority queue is a heap. Okay, so it basically just has slightly different member functions, and it's built as a heap inside. STL priority queue is probably going to be a little bit less code because it presents an interface where its member functions are essentially limited to exactly what you would need with a priority queue. But using the STL heap is not going to be very much code either. Both should be essentially the same speed because the STL priority queue, I'm pretty sure, is built on top of the heap. Okay, thanks for the heads up that you have a midterm at 6 on Thursday. I think I may ask the undergrad office so they can delay midterms to 6:10. I guess we'll see if that's doable or not. Let's see. Doesn't priority queue have a faster access time? I don't think so. So I'll go do a search afterwards. But basically, STL priority queue it's really like an interface. Underneath it is some data structure, and the normal data structure that you use for a priority queue is a heap. Okay, so it looks like that might be all the questions.